Hey there, everyone. My name is Ryan Schewel. Welcome to my analytics channel here on YouTube. So, in the case study today, I want to take a look at predicting construction cost overruns and schedule slippage and try to understand how this works. A lot of it has to do with project management, construction management, and things like this. I want to take a look at what goes on, underneath the hood here, and expose some things based on financials, operations, procurement, any kind of government contracts or protocols that a construction management company has to deal with, and execution out in the field too. How do you deliver? How do you meet expectations? And how do you go ahead and complete all the required construction necessities or mandates on time and hopefully on budget? We're not really going to focus too much on the financials, but more time to completion. Okay, so let's get into it. So I have the normal Python libraries over here. I'm going to import these just to allow me to do the analysis that I plan to do here. So I'm going to create a data frame with the project size, type, region, design maturity percentage, so on and so forth. We have things like materials index, wage index, weather in terms of rain days. We're going to try to quantify this. Permit lead days. This is important too, right? If you need permits and they're not in place, you can't do what you need to do, right? You can't break ground, you can't build a foundation, you can't build, you can't do anything if you don't have the permit. So we're going to look at that. Contingency percentages, float days. Are we on track? Are we ahead of schedule? Are we behind? How do we get there? How do we get back on track if we're off track? Things like that. Logistics complexity and start season month. So that has an impact too, especially if you're higher up in the northern hemisphere or lower down in the southern hemisphere, where you have seasons and big fluctuations in temperatures during the seasons, right? That could have an impact on your time to completion for your construction project. So here is the initial data frame, right? So indicating exactly what I referenced over here. So we have the data frame with all the features that are relevant to the study that we're doing. So we're going to look at a couple different, we're going to look at the base scenario here and modify this just a slight bit, just a tad bit, to see what's going to happen or what kind of impact we can anticipate here if there is a slight overrun in the scheduling, in paying the construction workers, the overall scope of the project, complexity in terms of logistics, in terms of operations, and in terms of supply chain, getting materials to the site, things like this, right? If there's a slight delay in some of these features or some of these inputs here to the model, what kind of overall impact is that going to have, right? Like, I want to try to quantify this and anticipate so we're not caught off guard and so we can plan accordingly, right? So we have all the targets, all the expectations. There could be slight cost overruns, right? Schedule slippage. Slippage is basically, okay, we plan to do whatever the construction plan calls for in 5 days. Maybe it takes 6. There's a 1-day slippage. Maybe it takes 7 and there's a 2-day slippage, right? So if we start to have more and more slippage and we're getting further and further behind, it's going to be harder and harder to catch up, right? We want to stay on schedule, on point, hopefully ahead of the curve a little bit, and deliver on time, on budget as expected, right? But if things go off course, if we deviate a little bit, then we have to self-correct, but it's going to be costly too if we get off the path here, okay? So control enter to run this, and we are capturing the basic metrics that we need to input to the model to make the forecast into the future. So we have the pipeline here. All the data is going to flow through the pipeline. We have the regular costs, regular time, classifying risk, and then we have the training testing. The Y is a dependent variable, so all the independent variables will have an impact on the dependent variable. Okay, so just keep that in mind. Independent is independent, and dependent is dependent on the independent variables. I have a bunch of videos on my YouTube channel that explains exactly how that works. If you don't totally understand it, Google it or check out some of those videos, and it should become apparent what's happening. So we're going to calculate the mean average error. the mean percentage error, and the R squared. This is the, what is it? The R squared is the coefficient of determination, right? To how closely we align with all the data points on the regression line aligns to what the average of the regression line is, right? So if all the points are way off the regression line, we're going to have a big R squared. If they're pretty tight, we're going to have an R squared close to 1, right? So the smaller the R squared, closer to 0, the more fragmented the outcomes are, the less predictable they are. The closer R squared is to 1, the more predictable they are, and the tighter they are to the average overall line, right? As you increase X, Y increases at a constant rate relative to the average line. So, okay, so we have our metrics here. Let me go ahead and run this and look at the table. Everything is going to be dumped into a table so we can quantify all the risks here, including the mean average error and the R squared, and see what these look like. And then use that with our risk classifier to determine the probability of risk here. Are we at high risk for running over the schedule, the predicted schedule, or are we going to be mostly on schedule and deliver on time, on budget, or are we going to be behind schedule, right? So we want to stay on schedule, or hopefully maybe even above schedule or ahead of schedule, right? So mean average error is pretty low. MAPE, kind of low, decent. R squared is a little bit lower than we'd like to see us at 0.7 or higher. So that just means R squared is the goodness of fit between all the independent variables and the average of all the independent variables, all averaged together. Let me see if I can find an example here. Let me see, images. R squared. And then plot this, but you can see from the illustration over here. So here's the average line. The red line is running between all of the green dots on the XY axis, right? The two-dimensional plot. And you can see there's kind of some deviation. There's not a super high R squared over here. This is probably a little bit better over here, a little bit tighter fit. We're looking for a goodness of fit close to 1.0. This is pretty close, right? It's showing a little bit deviation. This is going to have a low R squared, right? Everything is off. I was looking for something that has a really tight R squared. This has no predictive capabilities at all. This is just random, right? You don't want to see that. You want to see more of an outcome like this, where the average line indicates basically where all of the XY points fall pretty close to that line, right? So the higher the R squared, the closer to 1, and the better off we're going to be. This is a little bit low, but this lesson is not about R squared or tuning the model with different inputs, the hyperparameters, or using various different models. We could get to R squared up pretty easy. Not too concerned about that now. I'm just looking at the overall construction costs, any potential overruns, potential slippage, which is going to cause us to go into slippage territory, and how do we remediate that. So this is a metric that is useful, and we'll take that into consideration, but I'm not going to dwell on that too much, okay? So here are all the features in the data frame. So we're looking at project size, type, region, northeast, southeast. Remember, if it's in warmer regions, you don't have to deal with seasonality too much. Then you're probably fine. If you're high up in Alaska or Maine, or maybe northern Washington State, where temperatures drop quite a bit in the winter and they soar in the summer, you know, the variability of temperatures could have more of an impact on your construction site than if you just were in a more temperate zone. Permit lead days, rework days, contingency percent, logistics complexity, season start, overrun, potential overrun, and predicted cost overruns, and then predicted schedule slip days. Okay, so this is kind of the focus of the whole case study here today. The more the slip days, the more we're going to go over the budget that we've been allocated for, right? And it's going to cost more, and it's going to take longer to deliver the final product, which is a a finished construction site, right? So we have the mean average error. This is kind of low, about 3.4 percentage points. Nothing too crazy. That's fine. We can live with that. That's actually pretty good. 43% looks scary, but this is actually misleading here because targets are normally at 0% or negative, and anything can go above that pretty quickly and pretty easily. I'm not too concerned about this. R squared is fine. Again, a little bit low. We'd like to see a little bit higher R squared, 0.7 or greater, but this is not an R squared exercise, so I'm not going to lose any sleep over that. 0.85, this is strong. 0.965 is very strong. Closer to 1.0 is better. These are close to 1.0, so that's good. This, I'll let that slide. Again, not too concerned about it. Higher is better. We'd like to see that close to 1.0, but if it's 0.07, that's fine. That's fantastic. 0.05 is doable. We can live with that. So I had to refresh here. I lost my view. Okay, so get the view back. So the business aligned scoring is the MAE. This is the mean average error, and we're looking at the overall predictions, right, based on the inputs that we fed into the model and the outputs. Again, the independent variables are the inputs, so any kind of X variable is an input. The dependent is the target variable that we're trying to predict. Okay, so I think we're in a good spot. We have the data frames here, cost percent, cost overrun percent, slippage, schedule slip days, right? That's the slippage, and overrun risk flag. So these are the three target variables that we're trying to predict. Remember, the independent variables are independent. They can be anything. The dependent variables are dependent on the independent variables. These are the target variables or the predicted variables, right? So we're trying to predict overrun percentage. If there is going to be one, how much? We want to know that ahead of time before we start construction, and we can anticipate that and try to prevent overruns. We want to know slippage days. Again, understand what this could be, quantified as a slippage day, 1, 2, 3, 10, 20, 30. We want to know potentially what that could be and a certain probability around that. And then overrun risk flag. This is going to be a binary outcome. Overrun, yes or no. Are we going to be over, under, or right on target, right? So these are the target variables. These are the Y variables, cost, time, and cost, time, and just what we say, like classifier. This is going to be a classifier. The target classifier is risk flag, yes or no. So again, we see the three Y variables. We're dropping these from the data frame columns. So data frame drop that column. Target cost, that matches that right there. Target time matches that, and target classifier matches that. So the reason we remove these target variables is because we can't train the model on that. If the model is exposed to this, it's going to know what to predict. It's just going to memorize it and just spit back exactly what we already know. It's not going to learn anything or make any kind of prediction whatsoever, right? So we don't expose the model to the targets because we're trying to predict that. And again, we have a carve-out class. We have the training class, so it's going to be about 70 to 75% of the data that we run in the model, and we withhold about 30 to 25%. That's the holdout set for the testing. So we have the training, which has about 70%. The testing has about 30%. So the model can't see these things and memorize what's going to happen and just spit out a memorized answer. We want to learn based on unseen data and generalize to the rest of the population that it's not aware of because it hasn't been exposed to it yet. So hopefully that makes sense. If not, Google it and you should get your answers and fill in any knowledge gaps that you have. So there's the X train, X test, Y train, Y test, right? We have the cost, the time of the year, and all these things, all these variables that we set over here. These are the three target variables. So let's go ahead and run this and see what the data frame looks like. Okay, and yeah, again, we're looking at mean average error, R squared, area under the curve, and the precision, right? And we're gonna have to save this. You have to refresh this too because I noticed that down here it's getting skipped. Okay. Okay. The computer has some kind of amnesia here or some kind of Alzheimer's. I'm not sure which, but it tends to forget things pretty frequently. Okay, so here's the output here. So we have the cost, mean average error based, and the schedule. So here's the rework rate. This is going to take a little bit longer if we have to do things, if there was a mistake made we have to fix the mistake, remediate that, backtrack a little bit. Materials index, wages for the construction workers, maturity, contingency, scope, changes, seasonality, region, so on and so forth. So these are the potential things that could take the project off track. Has 20% chance of error, 9% goes down to about 0.0002%. So I'm not too concerned about this. The region where the construction project is occurring is not really going to have a significant impact whatsoever on the project, but materials index and rework rate, if something's done and it's not up to the the requirements or the needs or the specifications of the head construction manager, this has to be reworked, and that is going to take time to undo what was done because a mistake was made and you have to redo it. So let's get everything over here, cost overruns and schedule slippage days. Let me rerun this to refresh it. And I'm getting a mistake. None of the index overrun. Wait a minute, I might have been missing one. Let me go back here, take a step backwards. Okay, so now we get to some good stuff. So this is a SHAP plot that we're looking at. Basically, we're taking a couple different, not a couple, we're taking all of the independent variables from the X-train model. Remember, the independents came from over here, everything in the model except for, where is it? Except for target cost and target time and target classification, right? We're doing regression or classification. Usually, in this case, we're doing classification. So all of the target features over here are used to determine the predictive capabilities of the target variables. So everything except for cost, time, and classification is used in this in this SHAP plot. So we're trying to determine what features of all the features in the entire data frame are most likely to take this thing off course. How could we most likely drive into a ditch, or get thrown out off of the normal schedule, right? Things get disrupted or we get distracted or whatever. We have budget overruns and it takes longer to finish this project than we anticipated for. So what's the number one feature that we have to be most concerned about is the number of rework rates. So anything has to be reworked that was constructed inaccurately or incorrectly or something like this. It has to be undone, and whatever was built has to be deconstructed and then reconstructed. That is going to take the longest. Any kind of materials index. So materials coming to the site. So supply chain, potential supply chain issues, we have to be aware of that. Materials used in the construction project itself, we have to be aware of that. Wage index, right? So if wages of the construction workers changes, that can take us off course. If wages all of a sudden spike up because of some kind of union activities or whatever the case may be, maybe some people are walking off the project. They don't feel like they are making enough money. Now there's a bigger burden on the remainder of the workers, and they have to bear the brunt of doing more work with fewer people. And maybe the construction worker doesn't want to pay more. That could be a potential issue, right? Design maturity, any kind of contingencies, past performance scores. So these are the top items, top 5 or 6 items that can take us off course. The things that we really don't have to be concerned about is project type school. That seems pretty much irrelevant. Project type residential. If the project is a school or residential building, it shouldn't depend on the type of the construction. That's really not a non-issue, right? Like it's going to be built according to specifications of the construction contracts. Whether it's a school or residential, doesn't really matter. Contract type GMP. I'm not sure what GMP is. It just came up in the data. It's a different type of building. Apparently, if that is constructed that type, you have contracts for this. It just doesn't depend on the type of the building. What really could take this off course is reworking of things that have already been built. They have to be deconstructed, reconstructed, materials index, and wage index. These are the big three that could take us off course, right? So the rows show us the features after processing everything in this model. The features that have the most significant impact on either the project going longer, right, or maybe even finishing quicker, right? So if we can control those top 3 features, we control the outcome of the project. Each dot is one part of the project. The X is the SHAP value. The color is either red or blue. Red is high, blue is low. You can see mostly red to the right, blue is low. Horizon spread shows how strongly the features can move in the model. Greater than 0 is to the right, less than 0 is to the left. So we want more left to 0. Taking this down, or taking shorter time to completion. Again, the number of rework rates shifts predictions up to the right. Materials can shift it up or down, right? We want to try to keep that in the down area. Number of wage index, higher wages equal higher costs, and categorical codes have to be converted to, or non-numerical codes have to be converted to categorical codes or one-hot encoding. I didn't really address that issue, but you can see evidence of that over here. Okay, anything that is not numeric, if it's numeric, it's fine. Not numeric has to be categorically encoded. Okay, using a simple imputer or one-hot encoding. Slightly different approach, but kind of the same way to get a, that's really different actually. Like we're basically taking non-numeric values and converting it to categorical values, which are numeric, or some type of one-hot encoding. I don't think I actually did any one-hot encoding over here. It's really categorical, right? So the computer doesn't know what hospital, data center, or high-rise is. That has to be categorically encoded. This has to be encoded. These are numbers, so these are fine. These can be used as is. Anything that is not a number, like project type or contract type down here, has to be categorical encoded. Once it's encoded, we can feed that into the model, and the model can interpret that, okay? So we have one final data frame down here, which shows us predicted cost overruns, 80%, probability of an overrun. Okay, we always look at these things in terms of probabilities. It's not really overrun, yes or no. It could be, but you got a lot more insight if you say, at an 80% confidence level, am I going to hit an overrun, yes or no? So it's not just overrun, yes or no. Is it 80%, 90%, 95%? I want kind of percentages so I can understand what's the likelihood. Like yes or no could say overrun, yes or no. The overrun could be 1 day. I'm not super concerned about 1 day extra. If I have a 90% chance of the overrun happening for 20 days or 30 days, that's a month over, that would be more of a concern than 1 day, right? So I want to know the details. I want to know the probability of the outcome, not just the outcome, yes or no. I want more 25 days type of outcome. Predicted slippage schedule in days, 20, 31 days, 16 days, percentage, percent overrun likelihood, 18, 24, 22. So this gives me a lot more insight, 22 to 25% chance of overrun, and the number of days could be maybe 19 to 24 number of days. That gives me a lot more insight and a lot more knowledge and better information so I can make more informed decisions rather than overrun or not, right? These are overrun right here, 22%. Now I know what the overrun is. If it's just overrun, yes or no, I don't know, right? I want more insight. I want to know 19 days, not overrun. I want to know, is this 1 day, is it 19 days, or is it going to be 24 days, right? That's more useful to me than overrun or not. So that's what the table is showing. The last thing here I'll show you is we're looking at a chart to look at using Plotly and looking at time to completion. So this is sometimes called a Gantt chart. It shows you what a time frame is going to be in terms of duration, in terms of a horizontal bar. Here, all the orange represent predicted outcomes, and the blue show planned outcomes to finish. So a data center is going to take about early January until middle June to finish. That is the planned date. The predicted is going to go actually a little bit into July. So the predicted is a little bit longer than the planned. Same for the school. The planned starts about mid-January, goes until about mid-June. The predicted says no, it's going to go into about mid-July. The planned start for residential is about February, just after beginning of February. Again, predicted is a little bit longer than the planned, so it goes a few more days. We are saying start residential February 3rd, finish August 11th, start February 17th, finish August 22nd. Okay, so these are a little bit different. What was that? Wait a second, everything just flipped on me right there. Okay. And the last thing here is hospital, planned March 3rd and finish August 22nd. Planned March 3rd, finish September 20th. So the only takeaway in this view is all of these predicted time to completion for these construction projects are always longer than the planned. So I would just say to the construction manager or the team lead, whoever's in charge here, your plan always comes up short compared to the predicted model plan. So I understand, construction, supply chain, and time to deliver for a data center, a school, a residential, a hospital building. You'll know that, right? You've been doing this much longer than I have. I've never been in a construction business my entire life. I don't know the beginning dates and the intermediate dates and the end dates, but I know what the model is telling me. In all 4 cases, the predicted outcome represented by the orange bar is longer than the planned outcome. So I would just say, as a warning to the construction manager, maybe you know what you're doing, maybe you don't. Your planned project in all 4 scenarios is shorter than the predicted plan to completion based on the model that we tested and trained and fed in all the data based on historical information and historical time to completion. So I would just implore the construction manager to heed this predicted outcome and maybe scale up your planned days to completion a little bit. Maybe it comes in between your planned days, the blue bar, and the predicted days, which is the orange bar, and you can meet in the middle, okay? The predicted orange bar should be pretty accurate, and in all cases, it's going to take longer than the planned time to construction. So just be aware of that, and you don't want to be in an uncomfortable situation where you say you're going to plan to finish this data center on June 19th. The actual predicted plan end date is July 11th, not July 19th. It goes over almost a month. That's what the model's predicting. Just be aware of that and heed that warning, okay? Because if you say you're going to do it faster and it ends up taking longer, it's going to look bad. You're going to have budget overruns, frustrated stakeholders, right? Whoever's paying for this project, and you could destroy goodwill, right? If it takes a month longer to finish the project, which you pretty much guaranteed is going to be done by June 19th, and it actually takes until June 19th finish date, and actually takes into July 11th. That's going to be a couple weeks, about 3 to 4 weeks of uncomfortable conversations. You have to prepare for that if that's what you really believe. So that's it. That's my take on predicted construction cost overruns and schedule slippage using Python to do the modeling and the exact specific model that I picked. I think I kind of glossed over that. I don't think I addressed that. This is extreme test fit. Let me just look for the fit. Where's the model being fit? Okay. Oh, here it is, random forest classifier, okay? So random forest regressor for the numbers, regressor for numbers, and remember we're doing the classification for this model. This is the, this was the target closing, or target classifier, right? Overrun risk flag. This is the overrun risk flag, so that's a classifier. Will we overrun, yes or no? The other two are numeric, so we're using regression for that, schedule slippage days, and overrun cost percent, and slippage days. That's it, guys. That's my take on predicting construction cost overruns. I'm going to save this. I'm going to share all the source code with you guys so you have everything. Copy and paste it in your own environment and run it, and go ahead and make changes. Break the code, fix it. If you can't fix it and you get into a tight spot, just copy it over again and rerun it, and you'll have everything you need from the source code. Okay, so that's it, guys. I'm going to wrap it up. Thanks for your time. Appreciate it. This is the end, and I will post the video in the source code a little bit later today. I'm going to shut it off right now. We are at almost 30 minutes. That's long enough to do this thing justice. And I'll see you guys when I post the next video, which should be pretty soon. Okay, thank you for your time, and take care. Bye.